So here's something that might keep you up at night, except tonight, we're going to let it do the opposite. We're going to let it carry you gently toward sleep, because honestly, there's something deeply relaxing about a mystery this big. A mystery so enormous that it makes every other unsolved question in science look like a missing sock. And the mystery is this: most of the universe, and I mean the overwhelming majority of everything that exists, is made of something we cannot see, cannot touch, cannot bottle, cannot taste, and if we're being completely honest, cannot even properly name. We call it dark energy, which sounds dramatic, sounds like something from a comic book, but the name is really just a placeholder, a fancy way of saying, we have no idea what this is, but it's doing something extraordinary, and we need to call it something. Let's start there. Let's start with what dark energy is doing, because that's actually the part we're most sure about, and it's wild. The universe is expanding. You've probably heard that before. But here's the thing that changed everything. The thing that turned physics upside down in 1998 and hasn't let it recover since. The universe isn't just expanding. It's expanding faster and faster. It's accelerating. And that acceleration, is the thing that needs explaining. That's the fingerprint of dark energy. Something out there, woven into the fabric of space itself, is pushing everything apart, and it's winning. It's beating gravity, and gravity, as you know, is the force that holds galaxies together, that keeps your feet on the floor, that makes stars collapse into existence. Gravity is powerful, and yet, on the largest scales, something is overpowering it. Something is making the universe stretch faster with every passing moment. Now, to really understand why this discovery was so shocking, we need to go back. Way back. Not to 1998, when the discovery was announced, but to the early 20th century, when our entire picture of the universe was being built from scratch. And the person we need to start with, the person everyone starts with, and for good reason, is Albert Einstein. It's 1915, and Einstein has just finished his general theory of relativity. This is the big one, not special relativity, which he'd published a decade earlier and which was already revolutionary. No, general relativity is the full picture. It describes gravity not as a force pulling things together, the way Newton imagined it, but as a curvature in the fabric of space-time itself. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a dip, a curve, and if you roll a marble nearby, it spirals inward. That's not because the bowling ball is reaching out and pulling the marble. It's because the marble is following the curved surface. That's what mass does to space, according to Einstein. The Earth doesn't pull you down. The Earth warps the space around it, and you follow that warp. It's a completely different way of thinking about gravity, and it turns out to be spectacularly accurate. But here's where it gets interesting for our story. When Einstein applied his equations to the universe as a whole, not just to a single star or planet, but to everything, the entire cosmos, he ran into a problem. His equations told him the universe couldn't just sit still. It had to be either expanding or contracting. The math demanded it. A static, unchanging universe was unstable in general relativity, like a pencil balanced on its tip. It would have to fall one way or the other. And Einstein didn't like that. Nobody did, really. In 1917, the prevailing assumption was that the universe was eternal and unchanging. It had always been here, more or less the way it is now, and it always would be. That was the default. It wasn't based on evidence, exactly. It was more of a philosophical comfort. The idea that the universe might be expanding or collapsing felt absurd. So Einstein did something that he would later call his greatest blunder. He added a term to his equations, a fudge factor, a mathematical constant that he inserted specifically to hold the universe still, to counterbalance gravity and keep everything in a nice, stable, eternal equilibrium. He called it the cosmological constant, and he represented it with the Greek letter lambda. Think about what he was doing. His own beautiful equations were telling him the universe was dynamic, that it was moving, that it couldn't just sit there. And instead of trusting the math, he added an extra term to force the answer he expected. Now, to be fair to Einstein, he wasn't being lazy or dishonest. He had no observational evidence that the universe was expanding. Nobody did, not yet. And the cosmological constant wasn't pulled from thin air. It was mathematically legitimate. The equations of general relativity allow for it. It's a term you can add without breaking anything. But Einstein added it for the wrong reason. He added it because he couldn't imagine a universe that was anything other than static. And then along came Edwin Hubble. It's the late 1920s now, and Hubble is working at the Mount Wilson Observatory in the mountains above Pasadena, California, using what was then the most powerful telescope in the world, the 100-inch Hooker telescope. And Hubble is doing something remarkable. He's measuring the distances to galaxies. Now, at this point, the very concept of other galaxies is brand new. Just a few years earlier, there was a famous debate, the Great Debate of 1920, about whether those fuzzy spiral shapes in the sky were small nebulae within our own Milky Way, or whether they were entire separate galaxies, island universes, millions of light years away. Hubble helped settle that question. He found a way to measure the distance to what we now call the Andromeda Galaxy, and the number was staggering. It was far, far outside the Milky Way. The universe was suddenly much, much bigger than anyone had imagined. But Hubble didn't stop there. He also measured something else about these distant galaxies, their light. Specifically, he looked at the spectra of light coming from them, the way their light breaks down into different wavelengths, like a rainbow. And he noticed something strange. The light from nearly every galaxy he observed was shifted toward the red end of the spectrum. Red shifted. And here's why that matters. When a source of light is moving away from you, its wavelengths get stretched out, and stretched out light looks redder. It's the same principle as the Doppler effect with sound. You know how an ambulance siren sounds higher pitched when it's coming toward you and lower pitched when it's moving away? Light does the same thing, but with color instead of pitch. Red means moving away. So the galaxies were moving away from us, almost all of them. And here's the kicker. The farther away a galaxy was, the faster it was receding. Hubble published this relationship in 1929, and it's now called Hubble's Law. Though, to be completely fair, a Belgian priest and physicist named Georges Lemaitre had actually derived the same relationship from Einstein's equations 2 years earlier, in 1927. Lemaitre had predicted it theoretically. Hubble confirmed it observationally. Both contributions were essential, and for a long time, Lemaitre didn't get nearly enough credit. But that's a story for another time. The point is this. The universe was expanding. The galaxies weren't flying through space like shrapnel from an explosion. Space itself was stretching. Imagine drawing dots on a balloon and then inflating it. Every dot moves away from every other dot, and the dots that are farther apart move away from each other faster. That's what's happening to the universe. Space is the balloon. The galaxies are the dots. And everything is getting farther from everything else. When Einstein heard about Hubble's observations, he reportedly abandoned his cosmological constant almost immediately. If the universe was expanding, he didn't need lambda anymore. The fudge factor was unnecessary. The original equations, without the cosmological constant, naturally described an expanding universe. Einstein had been right the first time, and he'd talked himself out of it. That's why he called it his greatest blunder. Not because the cosmological constant was wrong mathematically, but because it had prevented him from making one of the most profound predictions in the history of science. He could have predicted the expansion of the universe years before Hubble observed it. So the cosmological constant was discarded, tossed aside. For the next 70 years, most physicists treated it as a historical curiosity, a cautionary tale about the dangers of letting your assumptions override your equations. The universe was expanding. Gravity was gradually slowing that expansion down. And the big question, the question that dominated cosmology for most of the 20th century, was whether the expansion would eventually stop. Would gravity win? Would the universe slow down, halt, and then collapse back in on itself in a big crunch, the reverse of the Big Bang? Or was the universe expanding just fast enough to escape its own gravity, coasting outward forever, getting colder and emptier and darker as the stars burned out one by one? Those were the two options: slow down and collapse, or slow down and coast. Either way, the expansion was decelerating. Gravity was the only game in town, and gravity pulls things together. The universe might expand forever, but it would always be losing speed, like a ball thrown upward. It might escape Earth's gravity if thrown hard enough, but it's always slowing down on the way up. That was the picture. That was what everyone expected. And to figure out which scenario was correct, collapse or coast, you needed to measure how fast the expansion was decelerating. You needed to look at very distant objects and figure out how the expansion rate had changed over time. And the best objects for that job, it turned out, were a very specific type of exploding star. They're called Type 1a supernovae, and they're special. Here's why. Most astronomical objects vary wildly in brightness. A dim star and a bright star look similar from far away. You can't easily tell if you're looking at a flashlight across the street or a searchlight across the city. But Type 1a supernovae are different. They all explode with roughly the same intrinsic brightness. They're what astronomers call standard candles. And the reason they're so uniform is fascinating. It has to do with how they form. A Type 1. A supernova happens in a binary star system, where a white dwarf, the dense, dead remnant of a star like our Sun, is slowly stealing matter from a companion star. The white dwarf gains mass bit by bit, and when it reaches a very specific threshold, about 1.4 times the mass of our Sun, a limit calculated by the brilliant Indian astrophysicist Subramanian Chandrasekhar back in the 1930s. It can no longer support itself. It collapses and detonates in a thermonuclear explosion so bright it can outshine an entire galaxy for a few weeks. Because they all go off at roughly the same mass, they all produce roughly the same amount of light. So if you see a Type 1a supernova that looks dim, you know it's far away. If it looks bright, it's closer. By comparing how bright it appears to how bright you know it actually is, you can calculate the distance. And by measuring the redshift of the galaxy it's in, you can figure out how fast that part of the universe is expanding. Do this for enough supernovae at enough distances, and you can map out the history of the expansion. You can see whether the universe has been slowing down, and by how much. That's exactly what two competing teams set out to do in the 1990s. One was called the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other was the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University, with Adam Rees doing much of the crucial data analysis. These two groups were rivals, racing each other to answer the same question: how fast is the universe decelerating? They were both expecting deceleration. Everyone was. The only question was how much. And then the data came in, and it made no sense. The distant supernovae were dimmer than they should have been. Not by a tiny amount, by a significant, unmistakable amount. Dimmer meant farther away than the models predicted. And the only way to explain that was if the expansion of the universe wasn't slowing down at all. It was speeding up. The universe was accelerating. Both teams found the same result, independently, using different supernovae and different analysis methods. They checked and rechecked. They looked for errors, for dust that might be dimming the light, for some systematic mistake in their measurements. Nothing explained it away. The acceleration was real. The announcement came in 1998, and it hit the physics community like a thunderbolt. This was not a minor correction. This was not a tweak to an existing model. This was the discovery that the universe is doing something that nobody predicted, something that requires a completely new component of reality to explain. Something was pushing the universe apart, and it was stronger than gravity. And the name they reached for, almost reluctantly, was the one Einstein had abandoned 70 years earlier: the cosmological constant, lambda. Except now it wasn't a fudge factor. Now it was something that might be physically real, something that might actually be out there, filling every cubic centimeter of space, exerting a gentle but relentless outward pressure that was winning the tug-of-war against gravity. And that shift, from mathematical convenience to physical reality, is one of the most profound things that has ever happened in the history of science. So let's sit with that for a moment, because it deserves some unpacking. When Einstein first wrote lambda into his equations in 1917, he wasn't claiming there was some mysterious energy filling the void. He was just adding a term to make the math behave. It was like putting a shim under a wobbly table leg. The table stands still. Problem solved. Don't think too hard about the shim. But now, 80 years later, these two teams were saying the shim might actually be something. The universe wasn't just expanding. It was expanding faster and faster. And the simplest mathematical way to account for that acceleration was to put lambda back into the equations of general relativity. Only this time, lambda wasn't keeping the universe still. It was driving it apart. So what does the cosmological constant actually represent, physically? Here's where it gets beautifully strange. If you take lambda seriously, if you treat it not as a fudge factor but as a real term in Einstein's field equations, then it corresponds to a uniform energy density that permeates all of space. Every point in the universe, whether it's in the void between galaxy clusters or right here in the room where you're lying, has this tiny but non-zero energy associated with it. Not energy from matter, not energy from radiation, energy that belongs to space itself, energy that's just there, baked into the fabric of the cosmos, and it doesn't dilute as the universe expands. That last part is crucial, so let me say it again a different way. Think about regular matter, stars, gas, dust, you, me, everything we can touch. As the universe expands, that matter gets spread thinner. The density of matter goes down because the same amount of stuff is occupying a larger volume. Same with radiation. Photons get stretched out. Their wavelengths lengthen. They lose energy. But this vacuum energy, this cosmological constant energy, doesn't thin out. It doesn't care that space is getting bigger. Every new cubic centimeter of space that comes into existence has the same energy density as every other cubic centimeter. So as the universe grows, there's more space, which means there's more of this energy, which means the expansion accelerates, which creates more space, which creates more energy. It's a feedback loop, and it's been running for billions of years. Now, you might be thinking, wait, doesn't that violate conservation of energy? Where's all this new energy coming from? And that's a genuinely deep question, one that physicists have wrestled with. The short answer is that in general relativity, energy conservation doesn't work quite the way you learned in high school physics. In a static, unchanging universe, sure, energy is conserved in the straightforward sense. But in an expanding universe governed by general relativity, the rules are different. The total energy of the universe is not a well-defined concept in the same way. It's not that energy conservation is wrong. It's that the concept gets slippery when space-time itself is changing. So the cosmological constant doesn't violate any law. It's perfectly consistent with general relativity. It's just deeply, deeply weird. And here's the thing that makes it even weirder. Quantum mechanics, the other great pillar of modern physics, actually predicts that empty space should have energy. This comes from the uncertainty principle. You can't have a perfect vacuum with exactly zero energy everywhere, because that would mean, both the value and the rate of change of quantum fields with perfect precision, and Heisenberg says, you can't do that. So even in supposedly empty space, quantum fields are constantly fluctuating. Particles and antiparticles are popping in and out of existence for unimaginably brief moments. And all of that activity contributes a baseline energy to the vacuum. This is called vacuum energy, or zero-point energy, and it's been experimentally confirmed. There's a real, measurable effect called the Casimir effect, where two metal plates placed very close together in a vacuum experience a tiny attractive force because of these quantum fluctuations. So you might think, perfect. General relativity says space can have an intrinsic energy density. Quantum mechanics says empty space does have energy. Problem solved, right? Lambda is just vacuum energy. Case closed. Except it's not closed. It's the opposite of closed. Because when physicists actually try to calculate how much vacuum energy quantum mechanics predicts, the number they get is wrong. Not a little wrong. Not off by a factor of 2 or 10. It's off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is, by some measures, the worst prediction in the entire history of physics. The quantum calculation says the vacuum energy should be so enormous that it would have ripped the universe apart, or crushed it, almost instantly after the Big Bang. The observed value, the one that matches the actual acceleration we see, is breathtakingly small by comparison. Almost, but not quite, 0. This discrepancy has a name. It's called the cosmological constant problem, and it has haunted theoretical physics for decades. Some people call it the vacuum catastrophe. And as of right now, tonight, as you're lying there listening to this, nobody has solved it. Nobody knows why the vacuum energy is so much smaller than quantum mechanics predicts. There are ideas, and we'll get to some of them, but no consensus, no breakthrough, no elegant resolution. It remains one of the deepest unsolved problems in all of science. But let's come back to 1998 for a moment, because the human story here is remarkable. Saul Perlmutter, Brian Schmidt, and Adam Rees, these three shared the Nobel Prize in Physics in 2011 for the discovery of the accelerating expansion. But in 1998, When they first announced the results, the reaction was a complicated mix of excitement and deep skepticism. Other physicists didn't just accept it overnight. The first instinct of the community was to look for mistakes. Maybe the supernovae weren't as standard as everyone thought. Maybe there was some kind of gray dust between us and those distant explosions. Dust that dims light without reddening it the way normal dust does. Maybe the supernovae billions of years ago were intrinsically different from nearby ones because the stars that produced them had different chemical compositions. These were all reasonable objections, and the teams had to address every single one. And they did. Over the next few years, as more data came in from more supernovae, from different telescopes, from different parts of the sky, the result held. Other independent lines of evidence started pointing the same way. Measurements of the cosmic microwave background, that faint afterglow of the Big Bang, showed a pattern that was consistent with a universe dominated by dark energy. Surveys of how galaxies cluster together on the largest scales told the same story. Everything was converging on a single, strange picture. The universe is about 68% dark energy, about 27% dark matter, which is its own mystery, and only about 5% ordinary matter. The stuff you and I are made of, the stars, the planets, everything we've ever seen or touched, is a tiny minority of what exists. Think about what that means for a second. We spent centuries building physics from the ground up, studying matter, understanding forces, mapping the periodic table, splitting atoms, smashing particles together at incredible energies. And all of that work, all of that knowledge, applies to roughly 5% of the universe. The other 95% is stuff we've never directly detected, stuff we named with placeholder words because we don't know what it is. Dark matter, dark energy. The dark doesn't mean it's literally dark, like the absence of light. It means it's dark to us, opaque to our understanding. We know it's there because of what it does, not because of what it is. And dark energy is the stranger of the two. At least with dark matter, we have a reasonable expectation that it's some kind of particle, something that interacts gravitationally but not electromagnetically, something that might one day show up in a detector deep underground or in a particle accelerator. People are actively searching for dark matter particles. There are experiments running right now as you're drifting off in abandoned mines and under mountains, waiting for a dark matter particle to bump into an atom of xenon or germanium. There's a plausible path to discovery there. But dark energy doesn't seem to be a particle. It doesn't clump. It doesn't interact with matter in any way we can detect except through its gravitational effect on the expansion of the universe. You can't bottle it. You can't shield against it. You can't build a detector for it. The only way we know it exists is by looking at the largest scales imaginable, billions of light years, and noticing that the expansion rate is wrong. It's too fast. Something is pushing, and we don't know what. So, after 1998, cosmology entered a new era. The old question, will the universe expand forever or collapse, was answered, but the answer raised a far deeper question. Not just whether the universe will expand forever, but why it's expanding faster and faster. And to try to answer that, physicists started exploring possibilities beyond the simple cosmological constant. Because here's the thing about lambda, it's the simplest explanation, and it fits the data beautifully. But it has that horrifying mismatch with quantum theory, and it has another property that some physicists find unsettling. Lambda is constant. It doesn't change. It's the same everywhere, at every time, forever. The energy density of the vacuum is just a number, fixed for all eternity, And while that's mathematically clean, it raises the question of why it has the particular value it has. Why not zero? Why not something larger? Why this exquisitely tiny, non-zero value that just happens to be relevant at this particular epoch in cosmic history? That question, why now, is called the coincidence problem. Because right now, in this era, the energy density of dark energy and the energy density of matter are roughly comparable. Dark energy is about 68%, matter is about 32%. They're in the same ballpark. But for most of the universe's history, that wasn't true. In the early universe, matter dominated overwhelmingly. Dark energy was negligible. And in the far future, dark energy will dominate overwhelmingly, and matter will be negligible. There's only a relatively narrow window of cosmic time when the two are comparable, and we happen to exist right in that window. Is that a coincidence? Or does it mean something? Some physicists think it's just a coincidence. After all, we can only exist when conditions allow for stars and planets and chemistry, and maybe that window naturally overlaps with the transition period. Others think it's a clue that the cosmological constant isn't really constant at all. Maybe what we're calling dark energy is actually something dynamic, something that changes over time, something with its own physics that we haven't figured out yet. And that idea, that dark energy, might not be a constant, but a field, something evolving and shifting, led to one of the most intriguing theoretical proposals in modern cosmology. It's called quintessence, and the name itself tells you something about how physicists were thinking about it, reaching all the way back to ancient philosophy. The classical Greek thinkers believed the world was made of 4 elements: earth, water, air, and fire. But there was a 5th element, a 5th essence, something purer and more fundamental that made up the heavens themselves. Aristotle called it ether, the quintessence. And when physicists in the late 1990s started looking for alternatives to a plain cosmological constant, they borrowed that old word, because what they were proposing was, in a sense, a new element of the cosmos, a 5th component of reality that nobody had detected directly, but that might be shaping everything. So let's talk about what quintessence actually is, because the idea is surprisingly elegant once you get past the jargon. Remember, the cosmological constant, lambda, is just a fixed number. It's baked into the fabric of space-time. It doesn't change, it doesn't evolve, it doesn't interact with anything. It just sits there, providing a constant energy density everywhere, forever. Quintessence says no, that's too simple. Instead, what if dark energy is produced by a field, a scalar field, specifically, that permeates all of space, but whose energy density can change over time? Think of it this way. Lambda is like a tax that's set once and never adjusted. Quintessence is more like a tax rate that responds to economic conditions, shifting up or down depending on what's happening. The universe evolves, and the dark energy evolves with it. Now, if you've heard the term scalar field before, it might sound intimidating, but you've actually already encountered one in popular science. The Higgs field is a scalar field. It fills all of space, it has a value at every point, and particles interact with it to acquire mass. Quintessence proposes something similar in structure. A field that fills all of space has a value everywhere, and that value can change over time as the field slowly rolls down its potential energy curve. Picture a ball rolling down a very gentle hill. The height of the ball on the hill corresponds to the field's energy, and as the ball rolls, the energy changes. If the hill is almost flat, the ball rolls very slowly, and the energy changes very slowly, and you get something that looks almost like a cosmological constant. Almost, but not quite. There's a subtle difference, and that subtle difference is, in principle, something we could measure. The idea was formalized in the late 1980s and through the 1990s by several physicists working somewhat independently. Christoph Vetterich published early work on a cosmological scalar field in 1988, before the supernova results even came in. Bharat Ratra and Jim Peebles at Princeton developed detailed quintessence models around the same time. And then, after 1998, when the acceleration was confirmed, the field exploded. No pun intended. Robert Caldwell, Rahul Dev, and Paul Steinhardt published an influential paper in 1998 that really crystallized the quintessence framework and gave it its evocative name. Steinhardt, in particular, became one of the most vocal advocates for the idea that dark energy is dynamic rather than static. Here's what's really clever about quintessence as a solution to the coincidence problem. Remember, the coincidence problem asks why dark energy and matter have comparable densities right now in this particular cosmic era. With a plain cosmological constant, that's just a brute fact. You shrug and move on. But some quintessence models have a property called tracking behavior. The scalar field doesn't just evolve randomly. It tracks the dominant energy component of the universe. When radiation dominated in the early universe, the quintessence field's energy density tracked along below radiation. When matter took over, it tracked along below matter. And then, at some point determined by the shape of the potential energy curve, the field's energy density catches up and starts to dominate. In these tracking models, the coincidence isn't really a coincidence at all. It's a natural consequence of the field's dynamics. The field was always destined to become important around this epoch, give or take. That's a much more satisfying answer if it's true. But, and this is a big but, quintessence has its own problems. For one thing, you need to specify the shape of the potential energy curve, and there are infinitely many possible shapes. Each shape gives you a different prediction for how dark energy evolves. Some curves give you dark energy that weakens over time. Some give you dark energy that strengthens. Some give you dark energy that stays nearly constant for billions of years and then suddenly changes. Without knowing the shape of the potential, quintessence is less a specific theory and more a framework, a family of theories. And that makes it harder to test definitively. You can't just say, quintessence predicts X. You have to say, this particular quintessence model with this particular potential predicts X. There's also a naturalness issue. To make quintessence work, the scalar field has to be extraordinarily light. Its mass has to be incredibly tiny, on the order of 10 to the minus 33 electron volts. For comparison, the electron, which is already one of the lighter particles we know, has a mass of about 500,000 electron volts. So the quintessence field would need to be lighter than the electron by a factor of something like 10 to the 38. That's not impossible, but in quantum field theory, keeping a scalar field that light is notoriously difficult. Quantum corrections tend to push scalar masses up. This is actually related to the hierarchy problem in particle physics, the same kind of issue that makes the Higgs boson mass puzzling. So, quintessence trades one fine-tuning problem for another. You solve the coincidence problem, but introduce a new question about why the field is so absurdly light. Still, the idea is compelling enough that it's driven a huge amount of observational effort. Because here's the thing, quintessence makes a specific, testable prediction that differs from a cosmological constant. It predicts that the equation of state of dark energy, the ratio of its pressure to its energy density, which physicists call W, is not exactly -1. For a cosmological constant, W equals exactly -1, always, forever. For quintessence, W is close to -1 but slightly different, and it changes over time. So if you can measure W precisely enough, and if you can measure how W changes with cosmic time, you can distinguish between a cosmological constant and quintessence. That's been one of the central goals of observational cosmology for the past 2 decades. And the measurements have been getting better and better. The Planck satellite, which mapped the cosmic microwave background with extraordinary precision, combined with data from baryon acoustic oscillations, those are the ripples in the distribution of galaxies left over from sound waves in the early universe, and combined with supernova data, all of these together constrain W to be very, very close to -1. As of the most recent analyses, W is consistent with -1 to within a few percent. No deviation has been convincingly detected, which means that so far, the boring answer, the cosmological constant, is winning. But so far is doing a lot of work in that sentence, because the error bars are still large enough that quintessence isn't ruled out. It's just not required by the data yet. Now, quintessence isn't the only alternative to a cosmological constant. There's a whole zoo of ideas, and some of them are wilder than others. Let me tell you about a few, because they show you the range of creative thinking that this problem has inspired. One idea is called phantom energy, and it's genuinely unsettling. In quintessence, W is greater than -1. It's something like -0.9 or -0.8. In phantom energy, W is less than -1, maybe -1.1 or -1.2. And that might sound like a small difference, but the consequences are dramatic. If W is less than -1, the energy density of dark energy doesn't just stay constant as the universe expands, it actually increases. The more space expands, the more dark energy there is per unit volume, which means expansion accelerates faster and faster in a runaway process. And if you follow that to its logical conclusion, you get what Robert Caldwell and his colleagues called the Big Rip. In a Big Rip scenario, the accelerating expansion eventually becomes so violent that it tears apart everything. First, galaxy clusters are pulled apart, then individual galaxies, then solar systems, then planets, then atoms. The fabric of space-time itself is ripped to shreds in a finite amount of time. Caldwell's original paper, published in 2003, estimated that if W were around -1.5, the Big Rip would occur roughly 22 billion years from now, which is comfortably far in the future. But still, the idea that the universe could end not with a whimper, but with a literal ripping apart of all structure is haunting. Now, most physicists regard phantom energy with deep suspicion, because models that produce W less than -1 tend to have serious theoretical pathologies. They often violate energy conditions that are considered fundamental, and they can lead to instabilities where the vacuum itself becomes unstable. But the observational data doesn't rule it out, and that's what keeps it in the conversation. When you measure W and you get -1 plus or minus a few percent, that error bar extends into phantom territory, so you can't ignore it completely. Another approach goes in a completely different direction. Instead of adding a new field or modifying the contents of the universe, what if the problem is with gravity itself? What if general relativity, Einstein's beautiful theory that's passed every test we've thrown at it, is slightly wrong on the largest scales? This idea falls under the umbrella of modified gravity theories, and there are quite a few of them. One of the most studied is called F of R gravity. In standard general relativity, the action, the mathematical quantity that you minimize to get the equations of motion, depends on something called the Ricci scalar, usually denoted R, which is a measure of the curvature of spacetime. In FR gravity, you replace R with some function of R, hence the name. By choosing the right function, you can get the universe to accelerate without any dark energy at all. The acceleration is built into the modified gravitational physics. It's not that something is pushing space apart. It's that gravity itself behaves differently on cosmological scales than it does in your living room. This sounds radical, but there's a precedent for it. Newtonian gravity worked perfectly for centuries until Einstein showed that it was an approximation of something deeper. Maybe general relativity is also an approximation, and on the largest scales, corrections become important. The challenge, of course, is that general relativity works spectacularly well in every regime where we've tested it. The solar system, binary pulsars, gravitational waves from merging black holes. Any modified gravity theory has to reproduce all of those successes while also producing cosmic acceleration. That's a very tight needle to thread, and most FR models that have been proposed end up being either ruled out by solar system tests or so close to general relativity that they're practically indistinguishable from a cosmological constant anyway. There's also a class of theories inspired by extra dimensions. If you've ever heard of string theory, you know that it requires the existence of additional spatial dimensions beyond the three we experience. In some models, our observable universe is a three-dimensional membrane, a brain, floating in a higher dimensional space called the bulk. And gravity, unlike other forces, can leak into the bulk. The DGP model, named after Gia Dvali, Gregory Gabadadze, and Massimo Parati, who proposed it in 2000, suggests that this leakage of gravity into extra dimensions could weaken gravity on very large scales, mimicking the effect of dark energy. It's an extraordinary idea that what we interpret as a mysterious repulsive energy is actually gravity escaping into dimensions we can't see. The DGP model made specific predictions that could be tested, and some versions of it have been ruled out by observations, particularly by the way large-scale structures grow over time. But the broader idea that extra dimensions could play a role in cosmic acceleration remains alive in various forms. And then there's something even more radical, an idea that questions whether we need dark energy at all. What if the apparent acceleration is an illusion caused by our position in the universe? This is the idea behind inhomogeneous cosmology models, sometimes called void models. The standard cosmological framework assumes that the universe is homogeneous and isotropic, the same everywhere and in every direction, on large scales. But what if we happen to live near the center of a large underdense region, a cosmic void? In that case, the expansion rate would be different inside the void than outside it, and when we observe distant supernovae, we might misinterpret the data as acceleration, when really we're just seeing the effects of living in an unusual neighborhood. This idea has been studied seriously, and it's largely fallen out of favor because it requires us to be suspiciously close to the center of a very large void, which violates the Copernican principle, the idea that we don't occupy a special place in the universe. It also struggles to simultaneously fit supernova data and CMB data. But it's worth mentioning because it illustrates just how far physicists have been willing to go to avoid invoking dark energy. The discomfort with a mysterious energy component making up 68% of the universe is real and deep. So, where does all of this leave us? We have the cosmological constant, simple, elegant, fitting the data beautifully, but plagued by the worst theoretical prediction in the history of physics and the nagging coincidence problem. We have quintessence, more flexible, potentially solving the coincidence problem, but introducing new fine-tuning issues and so far indistinguishable from lambda in the data. We have phantom energy, fitting the data but theoretically troubling. We have modified gravity, intellectually appealing but tightly constrained. We have extra dimensions, exotic and fascinating but hard to test. And we have void models, clever but probably wrong. What all of these alternatives share is that they're trying to answer the same fundamental question. Is dark energy a thing? Or is it a feature of the laws of physics themselves? Is it a substance filling space? Or is it a property of space? Or is it a sign that our theory of gravity needs updating? These aren't just academic questions. The answer determines the ultimate fate of the universe, whether it expands forever, whether it accelerates into oblivion, whether it eventually reverses course. And right now, in the early decades of the 21st century, we're in this remarkable position where we know dark energy exists. We know roughly how much of it there is. We know what it does, but we genuinely don't know what it is. And that's why the next generation of experiments matters so much. Because the way you distinguish between these models isn't through pure theory. It's through measurement, exquisitely precise measurement. And the instruments that are coming online right now, as you're lying here listening to this, are designed to do exactly that. One of the most ambitious is a space telescope that launched in July of 2023, a European Space Agency mission called Euclid. And what it's designed to do is map the shapes and positions of billions of galaxies across more than a third of the sky. That's the scale we're talking about. Euclid is essentially building a three-dimensional atlas of the universe going back about 10 billion years. And the reason that matters for dark energy is beautifully simple once you see it. Think of it this way. If dark energy has been constant over time, if it really is just Einstein's cosmological constant, lambda, sitting there at the same value forever, then the expansion history of the universe follows one very specific curve. But if dark energy is dynamic, if it's something like quintessence where the strength of the repulsion changes as the scalar field rolls down its potential, then the expansion history follows a slightly different curve. The differences are subtle. We're talking about variations of maybe 1% or 2% in how fast the universe was expanding at different epochs. But Euclid is designed to detect exactly those kinds of differences, and it does it through two main techniques that are worth understanding because they're genuinely clever. The first is called weak gravitational lensing. You know how gravity bends light. Einstein predicted that, and it was confirmed during the 1919 solar eclipse, one of the most famous experiments in history. Well, the same thing happens on a cosmic scale. When light from a distant galaxy passes near a massive cluster of matter on its way to us, the gravity of that cluster bends the light path slightly, which distorts the image of the distant galaxy. It gets stretched, sheared a tiny bit. Now, any single galaxy's distortion is too small to notice. Galaxies come in all shapes naturally, so you can't look at one slightly elongated galaxy and say, aha, gravitational lensing. But here's the trick. If you measure the shapes of millions and millions of galaxies in the same patch of sky, the random shapes average out, and what's left is the coherent distortion caused by the matter between you and those galaxies. It's like listening to a crowd of people all talking at once. You can't make out any individual voice. But if 1,000 people are all leaning slightly to the left because there's a strong wind, you can detect that lean statistically even though each person is also fidgeting randomly. So Euclid measures the shapes of about 1.5 billion galaxies. That's billion with a B. And from those shapes, it reconstructs where the matter is, how it's clumped together, and how that clumping has evolved over time. And that evolution is the key, because the rate at which matter clumps together under gravity depends on the tug of war between gravitational attraction, pulling things together, and dark energy pushing things apart. If dark energy got stronger over time, clumping would have slowed down more than you'd expect. If dark energy got weaker, clumping would have proceeded faster. The pattern of cosmic structure, the cosmic web of filaments and voids that galaxies trace out, is essentially a fossil record of how dark energy behaved over the last 10 billion years. That's what Euclid is reading. The second technique is called baryon acoustic oscillations, which sounds intimidating, but is actually one of the most elegant ideas in cosmology. Remember way back when we talked about the cosmic microwave background, that baby picture of the universe from when it was about 380,000 years old? At that time, the universe was a hot plasma, and sound waves were rippling through it. Literal sound waves, pressure waves in the plasma. When the universe cooled enough for atoms to form and the plasma became transparent gas, those sound waves froze in place. The regions that were compressed by the waves became slightly denser, and those slight overdensities became the seeds where galaxies eventually formed. The result is that there's a characteristic scale, about 490 million light-years in today's universe, at which galaxies are slightly more likely to be found near each other. It's like a preferred spacing, a subtle but measurable bump in the correlation of galaxy positions. Now, here's why that's useful for dark energy. That characteristic scale acts as a standard ruler. You know how long it is in absolute terms, because the physics of the early universe is well understood. So if you measure how big that ruler appears at different distances, at different points in cosmic history, you can figure out how the universe has been expanding. It's the same basic logic as the supernova standard candle method from 1998, but using a ruler instead of a candle. And because this ruler shows up everywhere in the distribution of galaxies, you can measure it at many different epochs and trace out the expansion history with remarkable precision. Euclid does both of these, weak lensing and baryon acoustic oscillations, simultaneously across an enormous volume of the universe. The mission is planned to run for about 6 years, surveying something like 15,000 square degrees of sky. Early data started coming in during 2024, and the first science results are being released as the mission progresses. What cosmologists are looking for in the data is the equation of state parameter W and, crucially, whether W changes over time. Because that's the real discriminator. Lambda predicts W equals -1, always, at every epoch. Quintessence predicts W is close to -1, but drifts slightly. Phantom energy predicts W is below -1. Modified gravity models predict specific patterns in how structure grows that differ from what dark energy models predict even when they give the same expansion history. So Euclid isn't just measuring one number. It's measuring a function, the behavior of dark energy across cosmic time. And Euclid isn't alone. There's a whole fleet of next-generation experiments either running or coming online in the 2020s, and it's worth knowing about the major ones because together they represent humanity's most serious attempt yet to figure out what dark energy actually is. On the ground, there's the Dark Energy Spectroscopic Instrument, DESI, which is mounted on the Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona. DESI started its main survey in 2021, and it's designed to measure the redshifts of about 40 million galaxies and quasars over 5 years. Redshift, if you recall, tells you how fast something is moving away from you, which tells you how much the universe has expanded since the light left that object. By mapping the three-dimensional positions of all those galaxies, DESI can measure the baryon acoustic oscillation scale at many different redshifts, many different epochs, and trace out the expansion history with extraordinary precision. And in fact, DESI released its first-year results in April of 2024, and they caused quite a stir. Here's what happened. The DESI team measured the baryon acoustic oscillation scale at several different redshifts and compared the results to what you'd expect if dark energy were a pure cosmological constant. And what they found was hints, tantalizing, preliminary, not yet conclusive hints that W might not be exactly -1, that it might be changing over time. Specifically, the data seemed to favor a model where W was less negative than -1 in the past, closer to maybe -0.7 or -0.8 at high redshift, and has been evolving toward -1 or even below -1 more recently. Now, I want to be careful here because the statistical significance was modest. We're talking about maybe 2 to 3 sigma, suggestive but not definitive. In physics, you generally want 5 sigma before you claim a discovery, which means the result is so unlikely to be a fluke that there's only about a 1 in 3.5 million chance of it being random noise. 2 to 3 sigma is interesting. It makes you sit up and pay attention, but it's not proof. Still, even the hint sent ripples through the cosmology community, because if dark energy really is evolving, if W really does change over time, that would rule out the cosmological constant. Lambda would be dead, or at least demoted, and something like quintessence or some other dynamical dark energy would take its place as the leading explanation. That would be enormous. It would mean there's a new field in nature that we've never detected directly, a field that permeates all of space and is slowly changing as the universe ages. It would open up entirely new questions. What is this field? What determines its potential energy curve? Does it interact with anything besides gravity? Could we ever detect it in a laboratory? But let's not get ahead of ourselves. The DESI first-year results are preliminary, and the full 5-year dataset will be much more powerful. And there are other experiments that will weigh in. The Vera C. Rubin Observatory, named after the astronomer who produced some of the most compelling evidence for dark matter back in the 1970s, is a ground-based telescope in Chile with an 8.4-meter mirror and the largest digital camera ever built for astronomy, a 3.2 gigapixel monster. When it begins its main survey, called the Legacy Survey of Space and Time, it will photograph the entire visible southern sky every few nights for 10 years. That repeated imaging means it can find and track enormous numbers of Type 1a supernovae, the same standard candles that Perlmutter, Schmidt, and Rees used in 1998. But instead of a few dozen, Rubin will find hundreds of thousands. With that, many supernovae spread across a wide range of distances, you can measure the expansion history with far more precision than the original discovery teams ever dreamed of. Rubin will also do weak lensing on a massive scale, complementing Euclid's space-based measurements with its own ground-based ones. Different telescope, different systematics, different sources of error, so if they agree, you can be much more confident in the result. And then there's the Nancy Grace Roman Space Telescope, NASA's next flagship space observatory, expected to launch around 2027. Roman has a field of view about 100 times larger than the Hubble Space Telescope, which means it can survey vast areas of sky quickly. One of its primary science goals is measuring dark energy through both supernovae and weak lensing, and it will push to higher redshifts than ground-based surveys can easily reach, probing the expansion history further back in time. So you've got Euclid in space doing lensing and baryon acoustic oscillations. You've got DESI on the ground doing spectroscopic baryon acoustic oscillations with tens of millions of galaxies. You've got Rubin on the ground doing supernovae and lensing. You've got Roman going to space to do supernovae and lensing at higher redshift. And there are others, the Simons Observatory and CMBS-4 for next-generation cosmic microwave background measurements, radio surveys like the Square Kilometre Array that will map hydrogen gas across cosmic time. All of these experiments are designed to measure slightly different things, using slightly different methods, with slightly different strengths and weaknesses. And that's deliberate, because in science, when you're trying to pin down something as subtle and important as the nature of dark energy, you don't want to rely on one measurement. You want multiple independent lines of evidence that either converge on the same answer, giving you confidence, or disagree with each other, which tells you something is wrong with your assumptions and sends you back to the drawing board. This is actually a beautiful moment in the history of this field, if you think about it. For most of the 20th century, cosmology was sometimes dismissively called the search for two numbers, the rate of expansion and the rate of deceleration. It was a data-starved field where theorists outnumbered observations. Now it's become precision science, with instruments that can measure the expansion rate to better than 1% at multiple epochs, that can map the distribution of matter across billions of light-years, that can detect the subtle warping of space-time by dark matter halos. The sheer volume of data coming in over the next decade is going to be staggering. And the question all of that data is converging on is deceptively simple. Is W equal to -1, or isn't it? Does dark energy change, or doesn't it? Because behind that simple question lies the deepest puzzle. If W really is exactly -1, if lambda is the answer, then we're stuck with the cosmological constant problem, that monstrous mismatch between theory and observation, and we have to accept that something about our understanding of quantum mechanics or gravity or both is profoundly incomplete. But if W is even slightly different from -1, if it evolves even a little, then the cosmological constant isn't the answer, and we need new physics, a new field, a new force, a new understanding of space-time itself. Either way, we learn something extraordinary. Either way, the universe is telling us something we don't yet understand. And that's what makes this particular decade so exciting for cosmology, even if you're hearing about it while drifting off to sleep. The measurements are being made right now. The photons are hitting the detectors. The data is being processed. And somewhere in that data, the answer might already be sitting, waiting for someone to extract it. Now, there's another angle on this whole problem that we haven't really explored yet, and it comes from a direction you might not expect. It involves the very fabric of space-time itself, and a concept that has fascinated and troubled physicists for over a century: the vacuum. What is empty space, really? Because when you strip everything away, when you remove every atom, every photon, every particle of matter and radiation, what's left? You might think the answer is nothing. Just nothing. A void. But that's not what modern physics tells us. Modern physics says the vacuum is anything but empty. It's alive. It's seething. And understanding what the vacuum actually is turns out to be absolutely central to the dark energy puzzle. Let's ease into this, because it's one of those ideas that sounds strange at first, but becomes deeply intuitive once you sit with it for a while. Think about a perfectly empty box. You've pumped out all the air, shielded it from every form of radiation, cooled it down as close to absolute zero as you can get. Classical physics, the physics of Newton, would say that box is now truly empty. There's nothing inside. The energy of that box is zero. End of story. But quantum mechanics says no. Quantum mechanics says you can never quite get to zero. And the reason comes from one of the most fundamental principles in all of physics, the Heisenberg uncertainty principle. You've probably heard of it in the context of position and momentum. You can't know both exactly at the same time. But there's another version of the uncertainty principle that applies to energy and time. It says you can't pin down the energy of a system to exactly zero for any finite period of time. There will always be tiny fluctuations, little blips of energy that pop into existence and then vanish again so quickly that they don't violate any conservation laws in any measurable way. These are called quantum fluctuations, or vacuum fluctuations, and they're not just theoretical. They have real, measurable consequences. Here's a beautiful example. In 1948, a Dutch physicist named Hendrik Casimir predicted something remarkable. He said that if you take two perfectly flat, uncharged metal plates and place them very close together in a vacuum, we're talking microscopically close, maybe a micrometer apart, there should be a tiny but measurable force pushing them together. Not gravity, not electrostatics, something else entirely. The idea is that the vacuum between the plates can only support certain wavelengths of these quantum fluctuations, only the ones that fit neatly between the plates, the way only certain wavelengths of sound resonate inside a pipe. But outside the plates, all wavelengths are allowed. So there's a slight imbalance. More fluctuation pressure pushing in from outside than pushing out from between the plates. And the result is a net attractive force, a force created by nothing, by the vacuum itself. For decades, this was a theoretical curiosity, a cute prediction. But in 1997, Steve Lamoureux at the University of Washington measured the Casimir effect directly, and it matched Casimir's prediction to within about 5%. Later experiments got even more precise. The vacuum really does exert a force. Empty space really does have energy. That's not philosophy, it's experimental physics. So here's where it connects back to dark energy. If the vacuum has energy, if empty space itself carries some intrinsic energy density, then that energy would behave in a very specific way when you put it into Einstein's equations of general relativity. It would act as a constant energy density everywhere in space, at all times. It wouldn't dilute as the universe expands, because it's a property of space itself. Every new cubic meter of space that gets created by expansion comes with its own vacuum energy built in. And when you work out what effect that would have on the expansion of the universe, you get exactly what we observe, an accelerating expansion. The vacuum energy acts just like a cosmological constant. It is, in a very real sense, the most natural candidate for dark energy. Space itself is pushing the universe apart, simply by existing. And this is beautiful. It's elegant. It connects quantum mechanics to cosmology in this profound way, except for one enormous, glaring, almost embarrassing problem. And we touched on this earlier. But now you can really feel the weight of it. When physicists actually try to calculate how much vacuum energy there should be, when they add up the contributions from all the quantum fields we know about, all the fluctuations at every possible wavelength, the number they get is absurdly, catastrophically large. We're talking about a factor of 10 to the 120 times larger than what we observe. That's not a rounding error. That's not even in the same universe, metaphorically speaking. If the vacuum energy were really that large, the universe would have expanded so violently and so rapidly that no structures could ever have formed. No galaxies, no stars, no planets, no you, no me. The universe would be a featureless, exponentially expanding void. So something is canceling out almost all of that vacuum energy. Almost all of it, but not quite. There's this tiny, tiny residual amount left over. This whisper of vacuum energy. And that's what we call dark energy. That's what's driving the acceleration. And nobody knows why the cancellation is so precise. Why does the universe leave behind exactly this much vacuum energy and not zero? Not some other amount? It's like the universe is balancing on a knife edge, and we don't know why. This is what physicists mean when they talk about the cosmological constant problem. And it's worth dwelling on for a moment, because it's genuinely one of the deepest unsolved problems in all of physics. It's not just that we don't have the answer. It's that every straightforward approach to getting the answer gives you something wildly wrong. The tools that work brilliantly for everything else in physics, quantum field theory, the Standard Model, renormalization, they all fail here. They give you infinity, or they give you that absurd number, and neither is right. Some physicists think the resolution might involve supersymmetry, the idea that every particle we know about has a heavier partner particle that we haven't detected yet. In a perfectly supersymmetric universe, the vacuum energy contributions from particles and their superpartners would cancel exactly, giving you 0, which is closer to the right answer than 10 to the 120. But it's still not right, because the vacuum energy isn't 0. It's that tiny positive residual. And besides, supersymmetry, if it exists, is clearly broken in our universe, because we haven't found any superpartners at the Large Hadron Collider despite years of searching, so the cancellation wouldn't be exact anyway. Others think the answer might lie in string theory. In the string theory landscape, this vast mathematical space of possible universes, maybe 10 to the 500 of them. Some of those universes would happen to have a small, positive cosmological constant just by chance. And maybe we live in one of those. This leads to the anthropic argument, which is one of the most controversial ideas in modern physics. The anthropic argument says, the cosmological constant has the value it has because if it were much larger, galaxies wouldn't form, and we wouldn't be here to measure it. We observe this value because it's the only value compatible with our existence. Steven Weinberg, Nobel laureate, one of the architects of the Standard Model, actually made a prediction along these lines back in 1987, more than a decade before the supernova teams discovered the acceleration. He argued that if the cosmological constant were real, it couldn't be much larger than a certain value, because above that threshold, structure formation would be suppressed. And when the actual value was measured in 1998, it was remarkably close to Weinberg's anthropic bound. That's either a profound insight or an extraordinary coincidence, depending on your philosophical disposition. But a lot of physicists are deeply uncomfortable with the anthropic approach. It feels like giving up. It feels like saying, we can't explain this value from first principles, so we'll just say it's an accident of which universe we happen to inhabit. It's not falsifiable in the traditional sense. You can't test it by experiment. And for a discipline built on prediction and falsification, that's a hard pill to swallow. So the debate continues, and it's one of those rare debates where the stakes are genuinely as high as they sound. We're arguing about the nature of reality itself, about whether the fundamental constants of our universe have explanations, or whether they're just what they are. Now, there's a related idea that takes this in a slightly different direction, and it's worth mentioning because it connects to some of the dynamical models we talked about earlier, quintessence and its cousins. Some theorists have proposed that the vacuum energy might not be truly constant, that it might relax over time. Imagine a ball sitting on a hillside. It rolls downhill, losing potential energy as it goes. Eventually, it reaches the bottom and stops. Some models of dark energy work like this. There's a field, and it's slowly rolling down its potential energy curve, and the energy it carries at any given moment is what we perceive as dark energy. If the field hasn't reached the bottom yet, then dark energy is still changing, still evolving, and the value we measure today is just a snapshot of a process that's still unfolding. This is essentially what quintessence models propose, but framed in the language of vacuum energy and its evolution. The field is sometimes called a slowly rolling scalar field, and if that phrase sounds familiar, it should. It's the same mathematical machinery that drives cosmic inflation, that brief period of explosive expansion in the very first fraction of a second after the Big Bang. In fact, some physicists have wondered whether dark energy and inflation might be related, whether the same kind of field that drove the universe's initial expansion might be responsible for the acceleration we see today, just operating at a vastly lower energy scale. It's a tantalizing connection, though nobody's made it work convincingly yet. And this brings up something subtle but important about the way physics progresses. Sometimes the biggest breakthroughs come not from answering a question directly, but from realizing that two questions you thought were separate are actually the same question in disguise. Inflation and dark energy, quantum mechanics and gravity, the vacuum energy problem and the hierarchy problem in particle physics. If any of these connections turn out to be real, if someone figures out how to link them, it would be the kind of unification that reshapes our understanding of everything. The kind of thing that happens maybe once or twice a century. But let's bring this back down to earth for a moment, because there's a practical dimension to all of this that's easy to miss. You might be thinking, okay, this is fascinating, but it's all so abstract, so far removed from everyday life. And in one sense, that's true. Dark energy operates on scales of billions of light years, over timescales of billions of years. You're never going to build a dark energy engine or a vacuum energy power plant. But in another sense, the quest to understand dark energy is driving some of the most remarkable engineering achievements of our time. The instruments we talked about, Euclid, DESI, the Vera Rubin Observatory, the Roman Space Telescope, these are engineering marvels in their own right. The detectors, the optics, the data processing pipelines, the statistical methods, all of it is pushing the boundaries of what's technically possible. And the techniques developed for cosmological surveys have applications in medical imaging, in machine learning, in signal processing, in ways that nobody anticipated when the project started. That's how fundamental science works. You chase a question because it's interesting, because you need to know, and along the way, you invent tools and methods that turn out to be useful for things you never imagined. The World Wide Web came out of particle physics at CERN. GPS depends on corrections from general relativity. and the algorithms being developed right now to extract the faintest cosmological signals from noisy data, who knows where those will end up? So here we are, in this extraordinary moment, where the biggest question in cosmology is also one of the biggest questions in fundamental physics. Is dark energy the cosmological constant, the energy of the vacuum, inexplicably fine-tuned to a value we can't explain? Or is it something dynamical, something evolving, something that might eventually change its character and alter the fate of the universe? And speaking of the fate of the universe, that's something we should really talk about, because the answer to the dark energy question doesn't just tell us about the past and the present, it determines the future. Everything about what happens next, on the grandest possible scale, depends on what dark energy actually is and what it does in the coming billions of years. So, let's talk about that. Let's talk about the end of everything. Now, when cosmologists talk about the fate of the universe, they're really asking a deceptively simple question. Does the expansion keep going? And if so, how fast? That's it. Everything else follows from the answer. And for most of the 20th century, the assumption was that gravity would be the deciding factor. The universe is expanding. Sure, Hubble showed us that, but all that matter out there is pulling on itself, trying to slow the expansion down. So the question used to be framed like this: is there enough matter in the universe to eventually halt the expansion and pull everything back together in a big crunch? Or is the matter density too low, meaning the expansion goes on forever, getting slower and slower, but never quite stopping? That was the old picture, and it was elegant in its simplicity. Two possible endings determined by a single number, the density of matter compared to a critical threshold. Above the threshold, the universe eventually collapses. Below it, the universe expands forever, but gradually decelerates. Right at the threshold, a kind of Goldilocks scenario where expansion asymptotically approaches zero but never reverses. Cosmologists spent decades trying to measure that density, and by the mid-90s the consensus was leaning toward a low-density universe. Not enough matter to stop the expansion. The universe would expand forever, but it would be a gentle, ever-slowing expansion. Stars would burn out, galaxies would fade, and the universe would drift into a long, cold, quiet darkness. That ending even had a name: the Big Freeze, or sometimes the Heat Death, borrowing from 19th century thermodynamics. And then 1998 happened, and everything changed, because the supernova teams didn't just find that the expansion was continuing, they found it was speeding up. And that changes the ending completely. If something is actively pushing the universe apart, making distant galaxies recede faster and faster, then the fate of the universe isn't just about whether expansion continues. It's about how aggressively it continues, and that depends entirely on the nature of dark energy. Here's where the equation of state parameter comes back. Remember W, that number we talked about earlier? The ratio of dark energy's pressure to its energy density. If dark energy is the cosmological constant, W equals exactly -1, and it stays at -1 forever. In that scenario, dark energy is a fixed property of space itself, constant and unwavering. The expansion accelerates, but it accelerates at a steady rate. And what happens in that case is actually pretty well understood. And it's worth walking through because it's both beautiful and melancholy, in a way that I think is genuinely moving, even if you're half asleep right now. In a cosmological, constant universe, the acceleration means that distant galaxies are moving away from us faster and faster. And here's the thing: there's a speed limit to how fast information can travel, which is the speed of light. So if a galaxy is receding from us fast enough, the light it emits will never reach us. It's not that the galaxy is moving through space faster than light. It's that the space between us is stretching so fast that photons emitted in our direction are actually getting farther away from us, not closer. There's a boundary, a cosmic horizon, beyond which we can never see, never communicate, never interact. And as the expansion accelerates, that horizon shrinks. Galaxies that are currently visible to us will, one by one, cross that horizon and disappear from view. Their light will redshift toward infinity, getting stretched to longer and longer wavelengths until it becomes undetectable. Think about what that means. Right now, we can see galaxies billions of light years away. We can study the cosmic microwave background from when the universe was only 380,000 years old. We have this incredible window into the history and structure of the cosmos. But in a universe dominated by a cosmological constant, that window slowly closes. Galaxies in our local group, the Milky Way, Andromeda, a few dozen smaller galaxies bound together by gravity, those will stick around. Gravity holds them together against the expansion. In fact, the Milky Way and Andromeda are on a collision course, expected to merge in about 4.5 billion years, forming a giant elliptical galaxy that astronomers have playfully named Milkomeda. But everything beyond the local group will eventually fade from view. A hypothetical astronomer living 100 billion years from now, in that merged Milkomeda galaxy, would look out at the sky and see nothing, just their own galaxy, surrounded by perfect, featureless darkness. No other galaxies, no cosmic microwave background. It would have been redshifted to wavelengths so long that no conceivable instrument could detect it. There would be no evidence that the Big Bang ever happened, no evidence that the universe was expanding, no evidence that billions of other galaxies ever existed. All the clues that we use today to understand cosmology would simply be gone. The universe would have erased its own history. That idea was explored beautifully in a paper by Lawrence Krauss and Robert Scherer in 2007, and it's one of those results that makes you sit with it for a while. It raises this unsettling philosophical question. Are we living in a special time? Not special in the sense that the laws of physics are different, but special in the sense that we happen to exist during the window when the evidence is still visible? 1 trillion years from now, the smartest civilization in the universe could do everything right, build perfect telescopes, develop flawless theories, and still reach completely wrong conclusions about cosmology because the data would simply be missing. They'd have no way of knowing what they were missing. It's a humbling thought. It suggests that our current understanding might be more fragile, more contingent on timing than we usually assume. But anyway, that's the cosmological constant scenario, the big freeze. The universe expands forever. Stars burn through their fuel over trillions of years. The last red dwarfs flicker out. Black holes slowly evaporate through Hawking radiation, over timescales so long, they make the current age of the universe look like a rounding error. We're talking 10 to the power of 67 years for a stellar mass black hole, 10 to the power of 100 years for the supermassive ones, and eventually, all that's left is a thin, cooling soup of photons and particles spreading out into an ever-expanding void, approaching but never quite reaching absolute zero. It's the ultimate heat death, maximum entropy. Nothing interesting ever happens again. Now that's if W equals -1, but what if it doesn't? Let's go the other direction first. What if W is greater than -1? That's the quintessence scenario, or at least some versions of it. If W is greater than -1, dark energy is still causing acceleration, but it's less aggressive than a cosmological constant. And in some quintessence models, W could even evolve over time, potentially increasing towards 0, or even becoming positive. If that happened, and this is speculative, but physically possible in certain models, the dark energy could weaken or even switch off. The acceleration would slow down, maybe stop. In the most dramatic versions, dark energy could decay away entirely, and you'd be back to a matter-dominated universe where gravity is the only game in town. The old question would reassert itself. Is there enough matter to cause a collapse? Some theorists have even explored models where dark energy eventually reverses sign, going from repulsive to attractive, which could trigger a big crunch after all, the universe expanding, slowing, stopping, and then contracting, getting hotter and denser until everything smashes back together. And there are cyclic models, notably developed by Paul Steinhardt and Neil Turok in the early 2000s, where this isn't the end, but a transition. The big crunch becomes a big bounce, and a new expanding phase begins, and the whole cycle repeats. An oscillating universe, breathing in and out over unimaginable timescales. It's a beautiful idea, though it faces serious technical challenges, and most cosmologists would say the evidence currently favors continued acceleration rather than eventual recollapse. But here's where it gets really dramatic. What if W is less than -1? What if dark energy is phantom energy, with an equation of state more negative than the cosmological constant? Remember, W less than -1 means that the energy density of dark energy actually increases as the universe expands. Let that sink in. In a cosmological constant universe, the energy density stays the same. Every cubic meter of space has the same amount of dark energy, and as space expands, you just get more cubic meters, so the total grows. But with phantom energy, even the density per cubic meter grows. The dark energy gets stronger and stronger over time. The expansion doesn't just accelerate, the acceleration itself accelerates, and that leads to the most violent possible ending, the Big Rip. This scenario was analyzed in detail by Robert Caldwell, Mark Kamienkowski, and Nevin Weinberg in a 2003 paper, and it's genuinely terrifying in an abstract, cosmic sort of way. Here's what happens. As the expansion rate increases without bound, it starts to overwhelm everything. First, galaxy clusters are torn apart. The expansion overcomes the gravitational binding between galaxies. Then, individual galaxies are disrupted, stars flung away from each other. Then solar systems, planets ripped from their orbits. Then the planets themselves, torn apart. Then atoms, then atomic nuclei. In the final instant, space itself is ripped apart at every point simultaneously. Everything that exists is shredded into nothing, and the timeline for this depends on how far below -1 W actually is. If W were, say, -1.5, the Big Rip would happen roughly 20 billion years from now, closer to -1, and you'd have more time. But eventually, inevitably, the rip comes. Now, you might be thinking, okay, but do we actually see any evidence for phantom energy? And the honest answer is, not really. The observations we have, including the latest results from DESI, are consistent with W being very close to -1. The DESI hints of evolving dark energy that we talked about earlier, those tantalizing 2 to 3 sigma signals from their first-year data, actually suggest W might be slightly above -1 in the recent past and slightly below -1 in the more distant past, which is interesting because it doesn't fit neatly into any simple category. It's not a clean cosmological constant. It's not clean quintessence. It's not clean phantom energy. It's something more complicated, something evolving, and the error bars are still large enough that the cosmological constant can't be ruled out. But that ambiguity is exactly what makes the next decade of observations so crucial. And here's something worth sitting with as you lie there. The fate of the entire universe, whether it freezes, crunches, rips, or does something we haven't even imagined yet, hinges on the precise value of a single number, and we don't know what that number is. We've measured it to maybe 5 or 10% precision, and within that uncertainty window, radically different futures are all possible. The difference between eternal cold darkness and the violent destruction of every atom in existence might come down to the third decimal place of W. That's extraordinary. That's the kind of thing that makes you understand why people devote their entire careers to building slightly better spectrographs and slightly more sensitive detectors. But the fate of the universe isn't just an abstract concern for far future cosmology. Understanding dark energy's behavior has implications for some of the deepest questions in theoretical physics right now, questions about the nature of space and time themselves. And one of the most fascinating developments in recent years has been the unexpected connection between dark energy and the nature of quantum information. Because it turns out that the same theoretical tools physicists use to study black holes and quantum entanglement have started shedding light on why our universe has a cosmological constant at all, and why it has the value it does. And this connection runs through one of the most celebrated ideas in theoretical physics over the last 30 years, something called the holographic principle. So let's talk about that for a second, because it sounds exotic, but the core idea is actually surprisingly graspable. The holographic principle says, roughly, that all the information contained within a volume of space can be described by a theory that lives on the boundary of that space. Think of it like this. Imagine you have a room, and inside that room there are objects, particles, fields, all kinds of stuff happening in 3 dimensions. The holographic principle says that everything happening inside that room, every detail, every interaction, can be fully encoded on the walls of the room. The 2-dimensional surface contains all the information of the 3-dimensional interior. It's not that the interior is an illusion, exactly. It's more that there's a deep equivalence between what's happening in the bulk and what's happening on the boundary. This idea didn't come out of nowhere. It grew directly from black hole physics. In the early 1970s, Jacob Bekenstein, a graduate student working with John Wheeler at Princeton, made a remarkable discovery. He showed that the entropy of a black hole, its information content, loosely speaking, isn't proportional to its volume, the way you'd expect. It's proportional to the area of its event horizon, the surface, not the interior. That was deeply strange. If you double the radius of a black hole, you don't double its information capacity. You quadruple it, because area scales as the square of the radius. But you've octupled its volume, so somehow the information is scaling with the surface, not the volume. Stephen Hawking initially resisted Bekenstein's idea, but in trying to disprove it, he ended up discovering Hawking radiation in 1974, which actually confirmed that black holes have entropy and temperature, exactly as Bekenstein had argued. And the formula they arrived at, the Bekenstein-Hawking entropy formula, became one of the most important equations in theoretical physics. Gerard 't Hooft picked up this thread in 1993, and Leonard Susskind developed it further. And together, they articulated the holographic principle as a general feature of quantum gravity, not just something special about black holes. And then in 1997, Juan Maldacena, a young Argentine physicist working at Harvard, made the whole thing concrete. He proposed what's called the ADS/CFT correspondence. Don't worry too much about the acronym, but it stands for anti-de Sitter space/conformal field theory. What Maldacena showed was a precise mathematical duality between a theory of gravity in a particular kind of curved spacetime and a quantum field theory living on the boundary of that spacetime with no gravity at all. Two completely different-looking theories that turn out to be secretly the same theory, just described in different languages. Now, here's where dark energy enters the picture, and here's why this matters for our story. The space-time in Maldacena's correspondence, anti-de Sitter space, has a negative cosmological constant. It's a universe that curves inward like the inside of a saddle. Our universe, the one we actually live in, has a positive cosmological constant. It curves outward. It's expanding and accelerating. And the mathematical tools that work so beautifully in anti-de Sitter space, all that gorgeous holographic machinery, they don't straightforwardly apply to our universe. This has been one of the great frustrations of theoretical physics for the last 25 years. We have this incredibly powerful framework for understanding quantum gravity, and it works in a universe that isn't ours. So, a huge amount of effort has gone into trying to extend holographic ideas to de Sitter space, the kind of spacetime that describes an accelerating universe with positive dark energy. And this is hard. Really hard. People like Andrew Strominger at Harvard proposed a version called DS/CFT as early as 2001, suggesting that the holographic description of our kind of universe might live on a boundary in the far future, at the end of time, essentially, rather than at the edge of space. But the details have been much harder to pin down than in the anti-de Sitter case. The boundary of de Sitter space is space-like rather than time-like, which creates all sorts of technical headaches. And the fact that our universe might not even stay de Sitter forever. Remember, if W evolves, the dark energy could change, makes the whole picture even murkier. But here's what's really fascinating. Some theorists have argued that the difficulty of constructing a consistent quantum theory in de Sitter space isn't just a technical problem. It might be telling us something profound about dark energy itself. In 2018, Qumrun Vafa at Harvard, along with collaborators Georges Obied, Hiroshi Uguri, and others, proposed something called the de Sitter swampland conjecture. And this stirred up enormous controversy. What they argued, based on patterns they'd observed in string theory, was that stable de Sitter space, a universe with a truly constant, positive cosmological constant that persists forever, might actually be impossible in any consistent theory of quantum gravity. The conjecture says that the dark energy in our universe can't be a true cosmological constant. It has to be something that changes over time. It has to be something more like quintessence. Think about what that means. If Vafa and his collaborators are right, then the nature of dark energy isn't just an observational question to be settled by telescopes. It's constrained by the fundamental rules of quantum gravity. The very consistency of the theory would demand that dark energy evolves, that W isn't exactly -1. And suddenly those DESI hints we talked about, those tantalizing suggestions that W might be changing, take on a completely different significance. They're not just interesting data points. They might be evidence for deep structural features of quantum gravity. Now, I should be honest with you. The swampland conjecture is far from proven. It's a conjecture, not a theorem, and plenty of string theorists disagree with it. There are constructions in string theory, the most famous being the KKLT construction by Kochru, Kalosh, Lind, and Trivedi from 2003 that claim to produce stable de Sitter vacua. Whether those constructions actually work has been debated fiercely for 2 decades. The arguments get incredibly technical, involving things like the stability of certain extra-dimensional geometries and whether quantum corrections spoil the classical solutions. It's one of those situations where brilliant people look at the same mathematics and reach genuinely different conclusions. But the fact that this debate exists at all tells you something important. It tells you that dark energy sits right at the intersection of observation and fundamental theory, and progress on either front could crack the other wide open. And there's another deep connection worth mentioning, one that ties dark energy to the very nature of space itself. Over the last decade or so, physicists like Mark van Ramsdonk, building on work by Shinsei Ryu, Tadashi Takayanagi, and others, have developed a remarkable idea that the geometry of space-time might emerge from quantum entanglement. The basic insight is that in holographic theories, the amount of entanglement between 2 regions of the boundary theory determines the geometric distance between the corresponding regions in the bulk spacetime. More entanglement means the regions are closer together. Less entanglement means they're farther apart. If you completely disentangle 2 regions, the spacetime between them literally tears apart. They disconnect. This is a beautiful idea, and it suggests that space itself isn't fundamental. It's woven from quantum information. And if that's true, then the expansion of space, which is what dark energy drives, might be deeply connected to how quantum information is organized on cosmological scales. Some researchers have started exploring whether dark energy could be understood as an entropic force, something that emerges from the thermodynamic properties of the holographic boundary. Ted Jacobson at the University of Maryland actually showed back in 1995 that Einstein's equations of general relativity themselves can be derived from thermodynamic arguments, from the relationship between entropy, temperature, and energy on causal horizons. If gravity is thermodynamic in origin, then maybe dark energy is too. Maybe the accelerating expansion is telling us something about the information content of the universe, about how the cosmic horizon encodes what's inside it. These ideas are speculative. I want to be clear about that. We're at the frontier here, where established physics gives way to educated guessing and mathematical exploration. But that's exactly what makes this moment in the history of cosmology so thrilling. The observational program, Euclid mapping the shapes of billions of galaxies, DESI measuring millions of spectra, the Vera Rubin Observatory about to open its eye to the southern sky, is converging with the theoretical program in a way that hasn't happened before. The telescopes might tell us whether W equals -1 or not, and that single measurement could confirm or rule out entire frameworks for quantum gravity. It could tell us whether the string landscape is real, whether the swampland conjecture holds, whether space-time is emergent, whether our universe is one of many. And you know what's quietly wonderful about all of this? Every one of these deep theoretical questions, holography, entanglement, the nature of space, they all come back to that same stubborn little number, lambda, that tiny residual energy of empty space that Einstein scribbled into his equations in 1917, then called his greatest blunder, and that the universe stubbornly insisted was real after all. A century later, it's still teaching us things we didn't expect. There's one more thread I want to pull on before we start winding down, and it has to do with something that might seem unrelated at first, but actually connects to dark energy in a surprisingly direct way. It's about the arrow of time, why time moves forward, why the past is different from the future, and what dark energy has to do with the deepest asymmetry in all of physics. Because here's the thing. Almost every fundamental law of physics works the same way whether you run time forward or backward. If you filmed two billiard balls colliding and played the footage in reverse, both versions would obey Newton's laws perfectly. There's nothing in the equations that says one direction is more real than the other. Electromagnetism, gravity, the strong nuclear force, even quantum mechanics at its most fundamental level. They're all time-symmetric. They don't care which way the clock runs. And yet, you and I know perfectly well that time has a direction. Ice melts in warm water, but warm water doesn't spontaneously form ice cubes. Eggs break, but don't unbreak. You remember yesterday, but not tomorrow. The universe clearly has an arrow of time, and the question of where that arrow comes from is one of the oldest puzzles in physics. The standard answer, the one you'll find in any thermodynamics textbook, is entropy. The second law of thermodynamics says that the entropy of a closed system, its disorder, roughly speaking, tends to increase over time. That's the arrow. Things move from ordered states to disordered states. Your coffee cools, your desk gets messy, stars burn out. Entropy goes up, and that's what gives time its direction. Fine. But that answer just pushes the question back one step. Because if the laws of physics are time-symmetric, then high entropy states are equally likely whether you go forward or backward. The only reason entropy increases toward the future is that it was lower in the past. The arrow of time doesn't come from the laws themselves. It comes from the initial conditions. It comes from the fact that the universe started in an extraordinarily low entropy state. The Big Bang was, thermodynamically speaking, an absurdly ordered beginning. And everything that's happened since, every star, every galaxy, every cup of coffee cooling on a table, is just the universe gradually relaxing toward higher entropy, toward equilibrium. Now here's where dark energy enters the picture, and it's genuinely surprising. Think about what dark energy does to the long-term fate of the universe. We talked about this, the big freeze, the heat death, the slow fade into a cold, empty, exponentially expanding void. In that final state, the universe reaches maximum entropy. Everything that can decay has decayed. Every black hole has evaporated. Every particle is so far from every other particle that nothing interesting can ever happen again. That's equilibrium. That's the end of the arrow of time, in a sense, because when you're at maximum entropy, there's no thermodynamic gradient left to drive change, no direction, no before and after that you could distinguish. But here's what's really interesting. The cosmologist Roger Penrose has thought about this more deeply than almost anyone. His argument, which he's been developing since the 1970s, is that the low entropy of the early universe is the central mystery of cosmology. Not dark matter, not dark energy, not the horizon problem or the flatness problem. The real puzzle is why the Big Bang was so special, so ordered. And when you think about what ordered means in a gravitational context, it's counterintuitive. For a gas in a box, high entropy means the gas is spread out evenly. That's the most disordered state. But for gravity, it's the opposite. A smooth, uniform distribution of matter is actually a low entropy state because gravity wants to clump things together. The highest entropy state for a gravitating system is a black hole. So the early universe, which was almost perfectly smooth and uniform, we know this from the cosmic microwave background, which is uniform to 1 part in 100,000, was in an incredibly low entropy gravitational state. That smoothness is what made everything possible. It's what allowed gravity to pull matter into clumps, forming galaxies and stars and planets, and eventually you, all while entropy steadily increased. Penrose's point is that no one has adequately explained why the universe started this way. Inflation, the theory that the universe underwent a brief period of exponential expansion in its first fraction of a second, is often credited with explaining the uniformity. And it does explain it, in a sense. Inflation smooths things out, stretches tiny regions to cosmic scales, irons out wrinkles. But Penrose and others have argued that inflation doesn't really solve the entropy problem, it just moves it. You need very specific initial conditions to get inflation started in the first place, and those conditions are themselves low entropy. You've traded one fine-tuning for another. So, what does this have to do with dark energy? Well, think about it this way. Dark energy determines the ultimate fate of the universe, whether it ends in a big freeze, a big crunch, or a big rip. And the ultimate fate of the universe determines the maximum entropy the universe can reach. In a universe with a positive cosmological constant, which is what we seem to have, there's a cosmological horizon, a boundary beyond which light can never reach you because the expansion is too fast. And just like a black hole horizon, this cosmological horizon has an entropy associated with it. It was Gibbons and Hawking who worked this out in 1977. The de Sitter horizon, the horizon you get in a universe dominated by a cosmological constant, has a temperature and an entropy, just like a black hole does. The entropy is proportional to the area of the horizon, measured in Planck units, and for our universe, that number is enormous, something like 10 to the 122nd power. And here's the kicker. That number, 10 to the 122, is essentially the maximum entropy our universe can ever reach. It's the size of the cosmic entropy bucket, if you like. The universe started with relatively low entropy, and it's been filling up that bucket ever since, and dark energy determines how big the bucket is. The value of the cosmological constant sets the ultimate thermodynamic ceiling of the cosmos. If lambda were bigger, the horizon would be smaller, the maximum entropy would be lower, and the universe would reach equilibrium sooner. If lambda were smaller, the bucket would be bigger, and the universe would have more room to evolve, more room for complexity, more room for interesting things to happen before everything winds down. So in a very real sense, dark energy isn't just determining the geometry of the universe or its expansion rate or its ultimate fate. It's determining the thermodynamic depth of the universe. How much entropy can be generated? How much complexity can arise? How long the arrow of time can keep pointing somewhere meaningful? That's a remarkable thing to wrap your head around. This one number, this tiny energy density of empty space, is connected to the most fundamental asymmetry in all of physics, the difference between past and future. And this connects back to something we touched on earlier, the idea that space-time might be emergent, that it might arise from something deeper. Entanglement, information, thermodynamics. If Ted Jacobson was right back in 1995 that Einstein's equations can be derived from thermodynamic reasoning, then the expansion of the universe isn't just a geometric fact, it's a thermodynamic process. The accelerating expansion driven by dark energy isn't just space getting bigger, it's entropy being produced. The cosmological horizon is radiating just barely at an incredibly low temperature, about 10 to the minus 30 Kelvin, unimaginably cold, but not zero. And that radiation represents the universe slowly thermalizing, approaching its final equilibrium state over timescales that make the current age of the universe look like the first tick of a clock. There's something almost meditative about that picture, isn't there? The universe, right now, in this moment, is somewhere in the middle of its great thermodynamic journey. It started in that improbable, low-entropy state, smooth, hot, dense, full of potential. And it's heading toward that final state, cold, empty, featureless, maximum entropy, all potential spent, and everything in between. Every star that burns, every planet that forms, every living thing that grows and thinks and wonders about the sky, all of that is powered by the entropy gradient, by the difference between the low entropy past and the high entropy future. We exist because the universe hasn't finished relaxing yet. We are part of the relaxation. And dark energy is the thing that sets the pace of that final act. It's the thing that determines how quickly the universe approaches its equilibrium. Right now, in our epoch, we're in a kind of sweet spot. The universe is old enough that structure has formed. Galaxies, stars, planets, complex chemistry, life, but young enough that the accelerating expansion hasn't yet cut us off from everything. We can still see the cosmic microwave background. We can still observe distant galaxies. We can still do cosmology. But as Krauss and Scherer pointed out, that won't last forever. The evidence is slowly being erased. The photons are being stretched, the galaxies are being pushed beyond our horizon, and future civilizations, if there are any, will look out at a sky that tells them almost nothing about the true nature of the universe they live in. There's a poignancy to that, I think. We happen to live at the one time in cosmic history when the universe is both complex enough to produce beings who can ask these questions and transparent enough to let them find the answers. A few billion years earlier, and the cosmic microwave background would have been too hot, too bright, too close to the surface of last scattering for anyone to have decoded its secrets. A few 100 billion years later, and it'll be gone, redshifted to nothingness, along with every distant galaxy and every clue about the Big Bang. We're in the window, right now, and dark energy is what's slowly closing it. So let me try to bring all of this together, gently, because we've covered a lot of ground tonight and you might be drifting, and that's perfectly fine. Here's what we know, and here's what we don't. We know the universe is expanding, and that expansion is accelerating. We've known about the expansion since Hubble in 1929, and we've known about the acceleration since those two teams, Perlmutter's group and Schmidt and Rees's group, measured distant supernovae in 1998 and found them fainter than they should have been. We know that whatever is driving the acceleration makes up about 68% of the total energy of the universe. We call it dark energy, which is really just a name for our ignorance, a placeholder for something we can detect but don't understand. The simplest explanation is Einstein's cosmological constant, a fixed energy density of empty space, the same everywhere, the same at all times, with a pressure-to-energy ratio of exactly -1. It fits the data beautifully, but it comes with that maddening theoretical problem. The value we'd predict from quantum field theory is off by 120 orders of magnitude from what we observe. That's not a small discrepancy. That's the worst prediction in the history of physics, and no one has solved it. Not yet. There are alternatives. Quintessence, a dynamic field that changes over time, that might have been different in the early universe than it is today. modified gravity theories that tinker with Einstein's equations on the largest scales. The string landscape, with its 10 to the 500 possible vacuum states, offering an anthropic explanation. Maybe our vacuum energy is small, not because of any deep principle, but because we couldn't exist if it weren't. The swampland conjecture, which says a true cosmological constant might be impossible in quantum gravity, which would mean the dark energy must be dynamic, must be changing, even if the change is too slow for us to have detected it yet. And then there are the deeper ideas, the holographic principle, suggesting that the information content of the universe is encoded on its boundaries. Emergent spacetime, where gravity and expansion arise from entanglement and thermodynamics. The arrow of time, rooted in the low entropy beginning, with dark energy setting the ultimate entropy ceiling. What's so beautiful about this moment in science is that all of these threads are converging. The telescopes going online right now, Euclid, DESI, Vera Rubin, the Simons Observatory, CMBS-4, eventually the Square Kilometre Array. They're not just measuring the expansion rate more precisely, they're testing whether W equals -1. And that single measurement, that one number, has the power to distinguish between a cosmological constant and quintessence, between general relativity and modified gravity, between the string landscape and the swampland. The data from DESI in April 2024, those tantalizing 2 to 3 sigma hints that W might be evolving, might not be exactly -1. They might be a statistical fluke, or they might be the first whisper of something extraordinary. We'll know more soon. The next data releases, the cross-checks with other surveys, the accumulation of evidence over the next decade. This is a story that's still being written. And I think that's a lovely thing to fall asleep thinking about. Not the answers, but the questions. The fact that right now, tonight, as you're lying here, there are telescopes on mountaintops and in orbit, quietly collecting photons that have been traveling for billions of years, photons that carry information about the expansion history of the universe, about the nature of empty space, about the deepest structure of reality. And somewhere, someone is writing code to analyze that data, or scribbling equations on a whiteboard, or lying awake just like you, turning over some idea about entropy or holography or the vacuum, trying to make it fit, trying to see if the math works out. We started tonight with Einstein in 1917, adding a single term to his equations because he couldn't accept a universe that moved. And we've ended up here, more than a century later, realizing that that term, that stubborn little lambda, might be the key to understanding not just the fate of the cosmos, but the nature of space and time themselves. It's been called a blunder, a mystery, a crisis, and a clue. It's probably all of those things, and the universe, in its quiet, unhurried way, is slowly giving up the answer. We just have to be patient enough and clever enough to listen. So let that settle over you. The universe is expanding, gently, steadily, carrying everything with it. The galaxies are drifting apart, the cosmic horizon is glowing faintly, the entropy is climbing, and time is moving forward. Because it has somewhere to go, because the universe hasn't finished its long, slow exhale. And you're here for it, part of it, made of the same stuff, riding the same expansion, asking the same questions that the universe seems almost to be inviting us to ask. That's not a bad thought to drift off with, not bad at all.